Hello students, in this video we'll find the maximum likelihood estimations for mu and sigma squared for a normal distribution with complete data. So given observations or realizations x1 through xn of x, which is normally distributed with mean mu and variance sigma squared for two parameters, let's estimate mu and sigma squared. Let's estimate mu and sigma squared by maximum likelihood estimation. By maximum likelihood estimation. One more O over there, hood estimation. Okay, so let's do it. So I'm going to take the normal distribution, where it is 1 over the square root of 2 pi sigma squared times e to the negative x1 minus mu squared over 2 sigma squared, and multiply it by itself a whole bunch of times by 1 over the square root of 2 pi sigma squared. And then what? Then e to the negative xn minus mu squared over 2 sigma squared. Okay, there we have it. That's the likelihood function. So this is our L. This is our function L. Depends on mu and theta. So I'm going to have two derivatives to do. So first thing I'm going to do is I'm going to find the little l of mu and theta by taking the logarithm of this. So if I log this, what will we have over here? We're going to have the log of this quantity over here. Now this quantity is a 2 pi sigma squared to the negative 1/2 power. So what will happen when I log that is we'll have a negative 1/2 log of 2 pi sigma squared. A whole bunch of times. How many times will we have that? We'll have that exactly n times. So I'm going to have n copies of that, because it's the same copy over and over and over again. Then when I log each of these exponentials, the exponential is going to go away, and I'm going to have the sum. J goes from 1 to n of what? Of xj minus mu. That's going to be squared over 2 sigma squared. Okay? This is the what? This function over here, and that's plus, of course. We're adding all these things up, so all these things are added together. So this is going to be my little l of mu and theta. And so let's do the derivatives of this problem. So let me first do the mu estimate. So if I do the derivative of little l with respect to mu, this is the derivative of the log likelihood. Well, this factor over here contains no mu. So these are really partial derivatives, so I should really update these to partial derivatives. So this is really a partial of little l. It won't matter for this problem, but partial of little l with respect to mu. This term will vanish because there's no mu's here, so I'll have what? I'll have the sum. J goes from 1 to n. And then I'm going to have a 2 xj minus mu with a negative sign over 2 sigma squared. That will be the expression we'll get by differentiating with respect to mu. And so I'm going to set this equal to 0 to find the maximum of this. And we can see that these factors over here, this 2 sigma squared and that negative 2, don't matter. What I'm going to get from this equation over here is if I sum these up, I'm going to have n times what? N times x bar by adding up all the xj's minus n mu is equal to 0. This is going to be my estimate. So this implies to solve this, that says that mu, the maximum likelihood estimation for mu, is just going to be x bar, the sample mean. So the maximum likelihood estimate for the mean is just the sample mean for normal distribution. Next, let's do the derivative of L with respect to, oh, this should be a sigma squared over here. So let's do sigma squared. Those are sigma squareds, not theta. So we have sigma squared. Sigma squared. Okay, and so let's do the derivative of little l with respect to sigma squared. So the derivative with respect to little l of sigma squared is going to be what? Well, now I have this term to do over here, so I'm going to have a negative n over 2. Negative n over 2. Then the logarithm does a what? I do the reciprocal of this, so I'm going to have a 1 over 2 pi sigma squared times 2 pi. The 2 pi will cancel out, so I'm going to get 1 over sigma squared. 1 over sigma squared. And then what? And then we will do the derivative of the sum with respect to sigma squared. So this is really what? I have the xj minus mu quantity squared, and I really have over 2, and then sigma squared is in the denominator, so that's really this thing over here. Looks exactly like what? That's really the same thing as xj minus mu squared over 2 times sigma squared to the negative 1. So the derivative of that will be what? So it's just sigma squared to the negative 1. So I'm going to have a plus the sum. J goes from 1 to n. And then we're going to have an xj, we'll have a -1. And then, so -1 xj minus mu squared over sigma squared, and then it's going to be quantity squared. So there's going to be a 2, and then there's going to be a sigma squared over here. And we're going to set this equal to 0. Now, one of the sigma squareds is going to cancel out, and one of the 2 will cancel out too. So one of my sigma squareds will cancel out. The 2 will cancel out. I'll throw the n on the other side. So I'm going to have, this tells me that n is equal to the sum. J goes from 1 to n of xj, and the negative cancels as well. Well, we can leave this negative. Xj minus mu squared over sigma squared. And now what do we have? And so now this will tell us, by solving for sigma, by multiplying by sigma squared and dividing by n, that sigma squared MLE is 1 over n, the sum, j goes from 1 to n, of xj minus mu squared. Now this is the what? This is the biased sample variance. So the bias of this estimator, of the sigma squared estimator for the maximum likelihood estimation, is non-zero, whereas the bias for the mu estimate in MLE is 0 because the sample mean is an unbiased estimator of the mean. So the biased sample variance is the MLE estimate for the variance for maximum likelihood estimation for a normal distribution, and the sample mean is the maximum likelihood estimation estimator for the mean for a normal distribution. Thank you very much.